Hello everyone, my name is Florian Mischek, and together with Philipp Danzinger we will talk about our work on the test laboratory scheduling problem, or TLSP for short. First, what is TLSP about? Well, as you can see from this example schedule, TLSP is a multi-project, multi-mode project scheduling problem where for a certain set of jobs we need to find an assignment of resources, starting time slot, and execution mode for each job. TLSP features constraints both typical to other project scheduling problems, for example, precedences between jobs or resource capacities that have to be upheld. But it also contains other constraints that are specific to this industrial test laboratory setting of TLSP. For example, instead of having homogeneous resources where each unit can be used for all jobs, each job defines a set of available units for each resource, and only those units can be used to perform the job. For example, employees need certain qualifications to perform each task. And that brings us to the probably most unique point of TLSP, and it is that the jobs themselves are not given as input, are not monolithic, but instead consist of one or several tasks. And all properties of the jobs have to be computed from the tasks that they contain. So the solver first has to find a grouping of tasks into jobs, and then find a schedule, so a resource assignment, starting time slot, and mode for each of the jobs. The general idea of these properties is that a job has to fulfill all requirements of each task over its whole length, which is the sum of the different task durations plus a certain setup time. For example, the available resources for a job are those that are available for all of the tasks that it contains. Of course, such a limitation means that the jobs are over-constrained. But on the one hand, this turns out not to be such of a limitation in practice, as most tasks that can be grouped have similar properties anyway. And on the other hand, it provides us with several advantages, including flexibility and robustness. If you're interested in the details of this formulation and the reasons behind it, I encourage you to contact us or visit our poster session.
Hello, I'm Philipp Danzinger, and I'm going to tell you about our solution approaches to TLSP. The first one is a constraint programming model, and the biggest challenge in developing this model was this grouping aspect, because the solver not only needs to group tasks into jobs, it then also needs to schedule those jobs. And of course, the requirements and properties and even the number of jobs can change depending on this first grouping step. Our model achieves this by identifying each job with a single representative task. Each task points at the representative task of the job it belongs to. These pointers are selected by the solver, so they are just an array of decision variables. On the slide there is an example of how this could look like, and in this case tasks 1, 2 and 4 all point at task 1, which means there is a job containing tasks 1, 2 and 4, which has task 1 as its representative task. Likewise, tasks 3 and 5 both point at task 3, which means there is a second job containing tasks 3 and 5 and having task 3 as its representative task. As a reminder, these pointers are only selected at runtime by the solver, and of course there are constraints in place to make sure they always represent a valid partition. For instance, when any task is pointed at, it must also point at itself. As a side note, you may have noticed that in this example, the representative task is always the first task of each job. This is not a coincidence, and this is also a symmetry breaking constraint used in our model. So, how can we now use this grouping to schedule the actual jobs? We do this by assigning resources and time slots to representative tasks. Let's take a look at two example constraints to see how this works. On a high level, the first constraint makes sure that a job is only assigned resources that are available to all of its tasks. The second constraint makes sure that each job is assigned enough resources to cover its most demanding task. The first constraint, covering resource availability, says for each task T and for each resource R, if R is assigned to the job of T, the representative task pointed at by T, then the resource must be part of the set of resources available to T. This means no matter which job T is now assigned to, that job becomes limited to the resources available to T. Now let's go over the second constraint, which makes sure that enough resources are assigned to each job. This one is a little more complicated, but let's go over it step by step. First of all, we quantify over all tasks T, and then on the left side of the equal sign, we say that the number of assigned resources, so summing over all resources, the number of resources assigned to T must be equal to the right side, and the right side being 0 if T does not point at itself. This means that tasks which are not representative tasks are simply assigned nothing. On the other hand, if T is a representative task, if it points at itself, the number of resources we need to assign is given by the maximal resource requirement of all tasks pointing at T. Now, you may be thinking that these constraints look pretty expensive, and I would agree. Putting together grouping and scheduling in a single model like this is not exactly easy on the CP solver. While the CP model does find valid schedules for most of our test instances, finding good solutions is best left to another approach. In addition to the CP model, we also developed a very large neighborhood search algorithm. This algorithm takes an existing schedule and repeatedly tries to improve it by generating and solving simple CP instances. These instances usually only allow one project to be changed, while all other projects have their grouping, their schedule, and their resource assignments completely fixed. The number of projects to reschedule can increase beyond 1 when the solver gets stuck. In addition, there is a to-do list to prevent unnecessary steps. Whenever a project or a set of projects was rescheduled, it becomes added to the to-do list and only removed once a potentially overlapping project has been modified. Finally, for some steps, the grouping is fixed completely to speed up the solver. Now I'll hand back to Florian, who will show you our results.
We evaluated our model on 33 benchmark instances, of which 30 have been randomly generated and 3 are real-world instances from our industrial partner. These instances have different sizes and properties and range from about 5 projects with around 30 tasks up to large instances with 90 projects and over 1,500 tasks. All these instances are available online, including the anonymized real-world instances. For our evaluations, we used a timeout of 2 hours, and in that time, CP managed to find 30 of the 33 feasible solutions. And then, since we use the CP model to generate the initial solution for VLNS, the same also holds for VLNS. As you can see, VLNS found far better solutions than CP, in particular for the larger instances. We also compare our results to a restricted variant of the problem called TLSPS, which we dealt with in earlier work. In TLSPS, a feasible grouping is already given as part of the input, and it cannot be modified by the solver. On the one hand, this provides the solver with additional information, and the fact that we know the grouping means that we can pre-compute job properties, which leads to a simpler model. On the other hand, the given grouping is not necessarily optimal, and a different grouping might actually yield better results. Indeed, in our experiments, we found better solutions with VLNS with flexible grouping for most instances, despite having a more complex model. This effect is even stronger when we allow the CP solver to use the known grouping of TLSPS for generating the initial solution for VLNS. To conclude our talk, In our paper, we described the first CP model for the complex real-world scheduling problem TLSP. This model includes a mapping between tasks to represent the variable number of jobs in TLSP. We also extended our earlier VLNS approach for TLSPS to also work with TLSP with flexible grouping, and we achieve better results in most cases, even without the knowledge of a feasible initial grouping. This also includes new best-known solutions for many of the large instances, including all 3 real-world instances. Finally, both our approaches have been deployed in the test laboratory of our industrial partner, where they are used in daily planning of lab operations. Thank you for your attention, and you're welcome to ask questions.